I'm Chris. I work at OVO Energy. I'm a Scala developer, and I'm going to talk to you about this technique called Bring Your Own Effect, which has become quite popular recently in a few more kind of functional Scala libraries like FS2 and HTTP4S. I've recently done the same thing for a library that I maintain called Scala Cache. So I'm going to explain what it is and how I implemented it and why you might want to think about it for your own code. So I'd like to start by reminiscing about the good old days before I started writing Scala. I was a Java developer for a long time, but I stopped. I guess it was around Java 6. And back then, futures existed in in Java, but they weren't used that widely because all you could do on them was call get, which just blocked until the future completed, so it wasn't that useful. So a lot of APIs would look a bit like this. So this is an interface for some kind of cache, takes keys and values, and you can see there's no futures or anything going on here. So if you call get and you pass in a key, it will just block until it can do some I/O potentially, maybe go across the network and talk to Redis or whatever and get the value. Maybe it'll fail, maybe it'll come back in 5 seconds, maybe it'll blow up and throw an unchecked exception, who knows. But at least it's simple. But then I started writing Scala, and suddenly you had to be reactive. Does anyone remember the Reactive Manifesto? Has anybody signed the Reactive Manifesto? I did, because you could click a little button and it was quite exciting. So I jumped on that bandwagon. So if you were going to write a similar API in Scala, it would probably look a bit more like this, and you'd have everything wrapped in futures. So you'll get, you pass in a key, gives you back a future, and at some point in the future that will complete, hopefully. It'll either complete or fail and you'll get your result. But then sometimes you don't want that. Sometimes that's just overkill. If, say, you're working with a cache implementation that is backed by caffeine or guava, it's in memory, it's not going to fail, it's not going to take 5 seconds to complete, it's going to take nanoseconds. So future is just really annoying to work with. So maybe you want to have like a future version, an async version and a sync version, have 2 different types of cache. And say that one that was backed by Redis would be an async cache and return futures, and one that was backed by caffeine would be a sync cache and would just return things as is, not wrapped up in a future. But then you have kind of 2 APIs that you have to deal with, which look very similar, except that one involves futures and one doesn't. Another way of looking at it is, instead of looking at like the implementation side, you can think of it from the perspective of the user of your library. Maybe sometimes they want to work with futures, and sometimes they just want to get the thing. They want to block their thread and get the value, throw an exception if something went wrong. It kind of depends on their use case. So maybe you want to implement it this way. So you have your interface for your cache returns futures, but then you have a separate API which wraps those up in a wait.result, so it deals with the futureness for you. And then you just get the value as is. And this is what I ended up doing in ScalaCache originally. For a long time, this is basically what the API looked like in ScalaCache. And I realized at the time that it's kind of rubbish. It's not very elegant. You've got these 2 very similar APIs, one just wrapping the other. It's hard to maintain these 2 different, well, similar but different APIs, and I don't know. I didn't like it, but I went with it anyway. But at least there's only 2 of them. There's the future version and the non-future version. So it's not like it's a massive maintenance headache. But wait. Here is a Scala Z user, and he doesn't like either of these alternatives. He wants to use Scala Z's task, which is a completely different kind of effect. It is a monad that defers its effects. So the problem, well, from his point of view, the problem with future is as soon as you create a future, it starts running and executing. So it's an impure effect. It's a side effect. You can't create a future and then just kind of leave it there and then later on say, okay, now please execute. You can't do that. So it's not possible to write pure programs using futures. You can't write a kind of description of what your program is going to do in a pure sense and then execute it later. So he wants to use Scala Z's task, which will allow you to do that. And then this is a cats user, and he wants to use the new cats effect IO monad, which is very similar. It's implemented differently, but it's the same idea. You can defer your IO until you actually are ready to execute it. So you can write a nice descriptive program that describes what you want to do and then execute it. Or maybe he's a Monix user, because Monix has its own monad called task. There's the new Scala Z IO coming out. There's all these different effect monads, which all basically do the same thing, but I don't want to support them all in ScalaCache. You don't want to have a bunch of different APIs that all do exactly the same thing with different monads. So the obvious thing to do is to abstract over that monad somehow. So this is a way of doing that. So all of our methods in the cache interface now take a type parameter f, and this f underscore syntax in square brackets. This means that f is a type constructor, so it's a higher kind of type, an f of something. So it might be like option or future or list or that kind of type constructor. So for some type constructor f, this get method will return an f of option of your value. And when you put something, it will return an f of unit. And then you can see a couple of examples of how a user of your library might use this. So if they are dealing with futures in their program, then they might call cache.get with future. Or if they're using Scala Z tasks, they'll do cache.get with task. One question is, how do you support this synchronous interface where you don't want your value to be wrapped up in anything at all? You just want the thing itself. You don't want a future or a task or anything. You just want an int. And the way that you do that is this little trick called Eid or ID or the identity monad. So you define a type alias id of a equals a, which just means that like an id of int is just int, for example. And then it turns out that you can define things like monad for this, and it works. So then if you want to get just a plain old int, you just call cache.get with id. And this trick of defining it as a type alias like this, it works most of the time in Scala. There's a few corner cases where the type checker just gets a bit confused, and it's quite frustrating, but in general, this works. So let's have a go at implementing a cache that uses this new abstracting over f mechanism. So we're going to implement a Memcache D implementation of the cache interface. We've got some kind of Memcache D client all set up, so we can talk to Memcache D. So if we wanted to implement the get method, we're given a key, and I guess we go and talk to Memcache D using the client, and we get the thing with that key, and maybe it exists, maybe it doesn't. And then we get that back from Memcache D, and then we somehow return it wrapped up in an f. But how do we do that? Because we don't even know what f is. It's completely abstract. We know nothing about f. So this isn't going to work. We need a little bit more information. So what we need is some kind of type class about f to be passed in implicitly. And this type class will expose some functions, some methods that we can use to do things like construct an f, given a value, lift it up into f, or given an f, like map over it, or flat map over it, or things like that. So assuming this type class has a method called pure, which takes a pure value and lifts it into f, then we could do something like this. We can call tc type class dot pure, pass in none, and it will just give us an f of none. So as long as we have the right methods on this type class, we should be able to implement a cache library. So the obvious question is, what type class do I actually want? And it kind of depends on what your library or your code needs to do. In general, you want to use the least powerful tool that will allow you to do what you need to do. So these are ordered in kind of increasing power as you go down. So we start with functor. That has a map method, which will take something wrapped up in an F, apply a function to it, and give you a new thing wrapped up in an F. That's not really enough power for us because we can't even create an F in the first place. So we need something that will at least lift some value into an F. And that's exactly what applicative does. So applicative extends functor, so it's got a map method, but it's also got this pure method, which means you can take a value, an int or whatever, and just wrap it in an F. Then increasing in power again, we've got good old Monad, which we all know and love. And what this provides is a flat map method, which has this signature here. I won't go into the details. Next one down, we've got Monad error, which extends Monad, but it gives you the concept of error handling. So you can raise errors, like something went wrong, and you can also recover from errors. So things like Future, Scala Future, that's got like a success case and a failed case. Or either, that's got a right case and a left case. Or try, that's got success and failure. They're all examples of Monad error. And then the last two, sync and async, this is where we start getting into effects territory. So sync has this method which I've called delay, which takes a thunk, which is it's a piece of code that will lazily be evaluated and in the end will give you something of type A. So the important thing is this little rocket arrow here. It's quite innocuous looking, but this is quite important. So this is a way of delaying your I/O, delaying your side effect. And this is what the Scala Z task and cats effect I/O and all of the other ones do. So this is, so you can take this chunk of side effecting code that like talks to the database or launches missiles or whatever, just wrap it in delay and it will be executed later when you want it to be. So you can control when it's going to be executed. And then async has this quite complicated looking type signature which takes in a function called register, which itself takes a callback, which is an either of throwable or A to unit, and also that thing returns unit, which really confused me for a while. I couldn't work out what this was doing, but I will explain it in a second. So a little aside on what we mean when we talk about async or non-blocking I/O. So there's a few different ways to do I/O. The most simple one, which we saw in Java land, was just to block the current thread. So you just you call out to database or whatever, you wait for it to come back, and when it comes back, you return your result. And if something went wrong, you throw an exception, I guess. And then a different way of doing it is to still block, but do it on a different thread. And an easy way to do that in Scala is to just wrap it in future. And that thing will take an execution context, which will specify which thread pool you want to use to run this future. So it's still eating up a thread somewhere until it completes. So it's using resources, but it's not the current thread. So your thread can continue to do work and respond to UI and things. But then the most powerful way of doing I/O, which you're probably interested in if you have really high scale and you want to handle thousands of requests a second or whatever, is event-driven async I/O. So this is where you say make the remote API call, but you pass in a callback which will be called when the thing finishes. So if you're using something like Netty, then for like low-level networking, then you might be used to this kind of mechanism, or Node.js does this a lot. And the idea is that this doesn't use any threads. It's very cheap to do. It doesn't use any, well, it does use some resources, but very few resources. because it's all based on these events. So when an event comes into your system saying that this function has completed, then your callback will be executed. And these things have a kind of total ordering of how powerful they are. So if we start at the bottom with this callback-based event-driven IO, this is the most powerful in the sense that you can wrap it up in this code here and turn it into a normal future that blocks a thread. But you can't go back the other way. You can't have code that is blocking a thread somewhere running in a future and just magically turn that into code that does everything using events and asynchronously and doesn't use up a thread. That's just not possible. And similarly, you can go from future to blocking the current thread by just wrapping it in a wait, but you can't really go the other way. So the point of this is that this is the most powerful tool that we can provide to people who want to implement things like caches and so on. So we want to use this mechanism, and if need be, we can kind of lift it into these other mechanisms later on down the line. But every time we do that, we're kind of losing information, so we can't go back. So that is what this async method is all about. So it takes in a function that takes in a callback and will actually call that callback at some point. So your function is going to do some I/O and eventually call the callback. And we'll see an example of this later on. So this is the type class that I went with for Scala Cache. It's quite similar to a type class with the same name, async, that's in Cat's effect library. But I had to make my own for various technical reasons. This is a very small example of an implementation, or sorry, an instance of this type class. So this is for Scala Future. I won't go into the details of this, but you can see that it's mostly delegating to methods that are already on Scala Future anyway. So like the map method, for example, just calls map on the future that's passed in. This is some real code from ScalaCache. So this is the caffeine implementation of the Cache API, and this is the get method. So this thing takes in, it's parameterized over this f, this type constructor. It takes in a key, and it takes in a mode, and a mode is just a wrapper around this async type class instance. So this mode.m, that is the async instance. And then on that instance, it calls delay. So if you remember, delay is the thing that lets you defer your side effects. So this whole block of code here, depending on what IO monad you decide to use, if you're using, say, Scala Z task or Cat's effect IO, this block of code will not run until you want it to. If you're using Future, then it will start running immediately, just like normal. I won't go into that, what it's actually doing. That's not the point. A slightly more complicated one, the Memcache D cache. So Memcache D implementation is wrapping a library called Spy Memcache D, which actually provides proper event-driven async I/O. So it gets to use this async function that I was talking about. So it takes in a callback, and it starts off an async get. This is using the Spy Memcache D. And when we add a listener to that thing, so when that thing completes in this onComplete method, if it's successful, we decode the value and we call the callback with the value. So you can see we're passing our result to the callback that we were passed in here. So this is again, this will not be called until the user decides they want to do their I/O. But when they do, then this is what happens. And this won't use up any threads. It's just all done based on events. So that was a kind of lightning tour of how I did this in Scala Cache recently. But you might be wondering, should I do this myself? It seems kind of complicated. Do I want to do this? I think there are good benefits to it. Firstly, if you're a library author, then as you've seen, it makes your library more flexible. It makes your library useful to more people, I guess. It's kind of worth noticing that this F that you decide to return in your API, this, if you restrict it to, say, Future, Scala Future, then that's a kind of implementation detail of your library that you're leaking to your user. So it's something that you can abstract over if you choose to. And if you do abstract over it like this, then it makes your library more versatile. So I think it's worth doing. And then if you are just building your own code, you're building an application, so you're basically the only user of your code. I still think it's worth doing, and I'll go through an example of how we did something similar in an application that we built at OVO Energy. So why I think it's worth doing, it gives you a kind of extra dimension of abstraction, which I'll explain a little bit, and it can also simplify how you write your tests. So the extra dimension of abstraction means that you can decouple these things. So generally, your business logic in most applications is just composing things, usually sequentially, like do this thing, and then do this thing, and then do this thing. Maybe with a bit of branching. But in general, it's just composing things in that way. Sometimes you can do things in parallel. So you can say, like, do these two things, and then combine the results, and so on. But again, that's just composition of operations. And that's the thing that you really want to be focusing on, I think, in most applications. So you want the code that does this composition to be as clear as possible and not cluttered by kind of implementation details. So an example of implementation detail is what monad you're using. Or generally, it's a monad anyway. So you might be doing things like error handling, using ethers, and passing context around using Kleisleys and things. So you can end up with quite a complicated, nested monad transformers and things, which can really clutter up your code if you're not careful. So it kind of decouples those things from each other. And then you've got the concrete implementation details, which is actually like sending queries to your database and so on. So this example that I'm going to go through, this is an application that's for managing users and their permissions. So you can do things like create a user or update a user's profile, that sort of stuff. So we've got a few traits here. I call these algebras. So we've got one algebra for persistence. So this is saving users to the database and finding them by ID and so on. We've got one for events. This is sending Kafka messages about like saying, I've just created this user, for example. So these are kind of the primitive operations, the kind of the atomic things that your application can do. You can think of each of them as like a mini DSL, I suppose. And then we can combine these algebras into a kind of higher level one. I've called it user ops, which will combine them sequentially. So all of these things are abstract in F, as you can see, but this user ops one, it imposes a constraint saying F has to be a monad. I don't really care what F is, but it has to be a monad so that I can compose them sequentially. And that means you can write them in a for comprehension. So the function to create a new user, it gets passed in some details about the user's name and address and so on. And then it just does these 3 steps. So it writes the user to the database, and then because of the details of the data store we're using, it gets back just an ID, and it has to then query the database and get the user that it just created. And then it sends a Kafka event saying, I've just created this user. So this is your business logic here. And then at the end, it returns the user. Next, you've got the choice of monad. So in our case, we have to deal with failure and return the appropriate HTTP response code and so on, depending on the type of failure. So we've got this user service failure trait, which could be, say, user not found or in some kind of internal error that we weren't expecting. So we've got our result of doing one of these operations is either a failure or some type A, say user, for example. But then we've got another layer of monadicity, if that's a word, because we've got some context that we want to pass into our function. This contains things like a trace token for the request so that we can put it into all of our logs and so on. So our monad ends up being a Kleisli which takes a context and returns a user service result of A. So Kleisli, if you've never heard of it, it's a kind of way of wrapping a function but allowing you to compose them sequentially. So it's a function. You can just think of it as a function from context to user service result of A. It's just a shame that everything's in the wrong order. So this is our monad. As you can see, it's quite complicated, but on the previous slide, when we were composing our operations, we didn't have to care about that. We just ran them one after the other. And then finally, we've got our concrete implementation details. So we've got a database that we need to talk to, and we've got our utility for publishing Kafka events and so on. And then we actually write our implementations here. Depending on how you like to structure your programs, you might find it a bit unsettling that we've kind of mixed everything into one class, and we've got user persistence stuff and sending event stuff going on in one place. You don't have to structure it like this. It's kind of, there's a few different ways of encoding this, but it's all basically the same idea. I think that's all I've got. Oh yeah, I was going to quickly talk about testing. I said that this can simplify your testing. And what I mean by that is that there's a couple of things. Firstly, that when you are testing things like this create user method, which does a few different things in turn, you are free to choose your monad here. You don't have to make it this complicated Kleisli of thingy. You can just say it's the identity monad, for example, which in your tests, which means it's a lot easier to construct and it's a lot easier to test the result. So that's one way that this can simplify your testing. Another is that, say you have a bunch of these different methods, one called create user, one for updating a user, one for changing a user's permissions and so on, and they all use these primitives, but they kind of use them in different combinations. You don't necessarily have to test every single one of them in detail. As long as you've got tests for each of these primitives, and you can kind of assume that monadic composition works as you expect, then maybe that's enough, depending on your particular requirements. So that's another way you can kind of save yourself some testing. I think that's all I've got. Oh yeah, so in conclusion, abstract early, meaning find these things that maybe you didn't even notice could be abstracted, like this F, and abstract over them as much as you can. And commit late, meaning commit to a concrete implementation as late as you possibly can when you're kind of wiring up your program at the very end.